Hi there, welcome to the 37th episode of the Synth project, where we are building a synth together. This is the day we complete the installation of the control voltage processor module and we start using it in our synth. Let's begin. Last time we finished assembling the first of the two PCBs for this module. Here is now the second of the two PCBs already mounted. Missing are all the components related to the digital LED voltmeter, since that is the only component of the module that is not duplicated. We are now going to do some work on the module case, and then we will start mounting it in the two PCBs. Here is the module case, which I already painted with a white glossy paint. I will have now to apply the decals and spray a few more coats of transparent paint on the panel to protect the decals. Here is the paper where I printed the decals using a color inkjet printer. Also, this paper has been sprayed with a few coats of transparent paint, this time to protect the ink from the water that will be needed to transfer the decals to the front panel. Take a look at the finished panel. All the decals have been applied as well as the transparent paint. Doesn't it look gorgeous? And now that the panel is finished, I applied some copper tape on the back for shielding purposes, and also to make sure that all the bodies of the components attached to the panel, potentiometers, switches and jack sockets, are all grounded together. Note how there is an area around the holes for the LEDs that does not have the copper tape, and that's because the LEDs, having a plastic body, don't need to be in touch with the ground, and also because I needed some naked plastic to make it easy for the hot glue that will hold the LEDs in place to stick to the surface of the back of the panel. Also, all the holes have been cleared from both the extra plastic sheet from the decals and the copper tape. So now the panel is ready for mounting the components to it, which I'm going to do offline. What do you think now of the completed panel, with all the components already attached to it? The potentiometers, the jack sockets, the switches, and of course the 10 LEDs for the digital voltmeter. Note the mess on the back with all the cables attached to the components and ready to be connected to the two PCBs that will be mounted on the side of the case. Let me now mount the first of the two PCBs to this side panel, and then I'll show you how it looks like. And here is the first PCB attached to the side panel of the module case, with the usual 4 spacers. Note how the PCB occupies most of the side panel surface, so it is impossible to mount two PCBs side by side. And in fact, the solution I implemented is to mount the two PCBs on top of each other, and that's why I am using more spacers in place of the usual screws to attach the PCB. These spacers are tall enough to make enough space between the two PCBs for the wiring of the first PCB to the front panel. Note that this PCB is the one without the LED voltmeter. This way we can have less wires packed in between the two PCBs. The voltmeter will be mounted only on the other PCB that will sit on top of this one. Given the amount of cables hanging around in the case, I want to make sure that they are all well set in place. To do that, I will connect all the wires for this PCB and I will test each element before attaching the second PCB. The wires that I will attach to this PCB are those that come from the right side on the front panel. The second PCB will take care of the left side and also of the voltmeter in the center. Here is the PCB with all the wires connected to it. Before testing this PCB, I will attach this plastic divider on top of the PCB to hold in place all the wires. Once they are not able to move anymore, I will test all the circuitry on this PCB before mounting the other PCB. The plastic divider will be held in place through these other spacers to make some space between the divider itself and the second PCB. Note how I did not use copper tape on this divider. The reason is that this circuitry is going to deal with high-level DC signals, and so any effect due to possible background noise is negligible, even without shield. Remember that the shield on the back panel is there to connect together all the mechanical component bodies, not too much for the actual shielding. Let's now start testing the first circuit on this PCB, the DC mixer. I have connected input 1 of the mixer to the output of the function generator, which is currently providing an all-positive sine wave at 1 Hz and peak value of 10 volts. The mixer output is instead connected to the first channel of the oscilloscope, where we can see how the wave is shaped. And of course, it is also a sine wave, in this case with about 5 volts peak, because the level of input 1 of the mixer is set to 50%. If I now change the level at the input, you can see how the output changes amplitude as well. Now I am going to leave the level set to 50% and I am going to play with the offset control. See how the wave remains basically unchanged, but is translated toward the top of the screen? Let's now test the second mixer input. And yes, it works as well, both with the shape of the wave, its amplitude, and the changes on the offset. Let's go now to input 3. And things work well too. I'm now going to test the inverted output. And you can see how now the wave is positioned toward the top, and when I increase the amplitude, it grows from the bottom rather than the top. And the effect of the offset is of course to push the wave toward the bottom. All seems to be good, and so let's test the next circuit, the glide. Here is the setup for this test. The input is connected again to the function generator, and the output is connected to the oscilloscope. The time control is set to the minimum and the switch is set to fast. The function generator is set to provide a ladder-shaped signal going from 0 to 10 volts with a frequency of 0.1 Hz. Let's now take a look at the oscilloscope. To better see what is going on, let me move the 0-volt line to the bottom of the display like this, and now I can increase the sensitivity of the channel to 2 volts per division. So here is how the signal looks like with the shortest possible glide time. Let me now increase the time a little bit, and you can easily see the effect on the signal. Now let me move the time control to the minimum again, but I will also switch the time base to the slow position. You can now see how the signal is affected immediately, even though the time settings on the potentiometer is to the minimum. Increasing now the time, and look what is happening. Very well, the circuit seems to work just fine, and so let's test the next one, the sample and hold. To test this circuit, I have again the function generator and the oscilloscope connected to the input and the output of the circuit respectively. I also have a third connector to insert the trigger signal into the sample and hold. Such trigger comes from this little device that we have already seen in the past, which sends a trigger signal every time I push the button. The function generator produces now a sine wave at 0.1 Hz, all positive, with a peak value of 10 volts. Let's take a look at the oscilloscope now, and basically every time I generate a trigger, the output takes the value of the sine wave at that very instant and holds it until a new trigger is generated. Let's now make sure that the trigger through is also working, and for that I am moving the oscilloscope probe from the output to the through socket. And yes, every time I push the trigger button, we can see that a trigger is visible on the through output, so that works too. The last circuit to test is the limitator. At the input of the circuit we have again a sine wave at 10 volts peak. And while we keep the level of the signal set to the max, we can see such a wave on the oscilloscope. But now, if I decrease the level using the limitator control, the sine wave changes its peak value, although keeping its original shape. Perfect. Let's now take care of the second PCB. It is installed directly on the spacers coming from the plastic divider, and it needs to be oriented the same way as the first one. Since we don't have to add any further element to this stack, this time we can use simple screws to attach the PCB. Once the PCB is mounted, we can start connecting the wires. I mounted first the voltmeter wires. First I connected all those from the LEDs, making sure I put them in the correct sequence, so they are illuminated in order from bottom to top when the voltage of the input increases. Then I connected the input wires and the through wires, and finally I connected the switch wires. As for the previous PCB, all the wires need to be laid neatly with the help of some zip ties. To test the LED voltmeter, I connected the input to a DC power supply, visible here on the left side. The through jack is connected to a multimeter set to measure volts, so we can both verify that the through output works fine, and we can easily read the input voltage on the multimeter, which has a higher precision than the voltmeter under test. The range switch is set to 10 volts, and so we have only one LED in the on state, since the voltage provided to the voltmeter input is 1.3 volts. Now, incrementing the input voltage, the number of on LED increases, reflecting the integer value of the current input voltage. Right now, for example, we have an input voltage of about 7.1 volts, and we see 7 illuminated LEDs. And finally, when the input voltage reaches the 10 volt threshold, all the LEDs are on. If we now lower the voltage back to the minimum available on the DC power supply, we can switch to the 1 volt range and see that the LEDs are also illuminated according to the voltages between 0 and 1 volt. I just noticed, however, that when the voltage goes below a certain threshold, although the correct LEDs are illuminated, there is an extra LED also illuminated, the 6th from the bottom. I'm not sure why that is happening right now, as it should depend exclusively on the IC LM3914. At this point I decided to move on to finish the module, but I will go back later and try to figure out why there is this problem and how to fix it. For now, we just have this annoying LED that turns on at the wrong time, but fortunately we can still have a read of the voltage. Let's now move to the next circuit, which is the mixer. I just connected all the wires from the panel to the PCB for the mixer part. There are wires for 4 potentiometers, 3 inputs, 1 output and 1 inverted output. Let's test this DC mixer now. I have an input jack connected to the function generator and the output connected to the oscilloscope. To have a better understanding of what is going on with the mixer, I set the function generator to provide a sine wave at 10 Hz going between 0 volts and 10 volts. The oscilloscope does not show anything right now, because the input level of the mixer is set to 0. So let's increase the level and watch what happens on the oscilloscope. And the sine wave increases and decreases in amplitude according to the changes on the potentiometer level. Let's now add some offset. And the whole sine wave is translated toward the top of the screen. And when we remove the offset, it goes back down. Moving now the oscilloscope probe from the output to the inverted output, we see that the sine wave is now on the top portion of the screen, and increasing the level, the amplitude increases, but toward the lower part of the screen, as expected. And of course, if we now add some offset, the whole sine wave moves downward. Let's now move the jack from the function generator to the second input. And the overall behavior remains the same. Let me now move the input jack to the last mixer input. And again, the overall behavior remains the same, both while changing the level and while changing the offset value. At this point, I have connected the wires for the sample and hold circuit. Here they are going from the back of the panel to the right side of the PCB. Here are the connections on the front panel to test the sample and hold. I have an input coming from the function generator, an output going to the oscilloscope, and a trigger signal coming from the contraption visible on the bottom right of the screen. The circuit is currently disabled since the switch is on the off position, and therefore the same sine wave that we see produced on the function generator is visible on the oscilloscope. Moving the switch to the on position, the output now generates a value equal to the one of the sine wave at the moment of the switch. Generating now triggers with a push button on the contraption, we see that the output voltage keeps changing to the new instantaneous values of the sine wave in those moments. However, I see a little anomaly. When the signal is left alone for a long time, it tends to increase, as if the capacitor that holds the voltage value keeps being charged. Well, for short period of times this is really negligible for now, so again I will not do anything and will give priority to completing and installing the module on the rack. But I will come back later to fix this problem, when I will work also for the other problem on the voltmeter. Other than that, everything seems to work fine. Let's now work on testing the glide circuit, for which I have already connected the wires on the back. The glide input is again connected to the function generator, and the output is connected to the oscilloscope. The switch is set to fast, and the glide time is set to the minimum. Here on the oscilloscope we can see a square wave, which is what the function generator is currently producing. Since the glide time is set to the minimum, the wave is almost unchanged. But now I am increasing the time, and we can immediately see its effects on the square wave. Let's switch to the slow range. Immediately we can see an effect applied to the signal, and increasing the time, the effect becomes more and more prominent. And so basically the glide circuit works too. Now it is time to connect the wires for the limitator. Input, output, and potentiometer. Time to test this last circuit too. The limitator potentiometer is currently all the way to the left, which means that the output signal should be at its minimal possible, practically zero. Input and output are again connected respectively to the function generator and the oscilloscope. The function generator is currently producing a sine wave. Let's see what the oscilloscope shows us. Rotating the limitator adjustment to the right, and the level of the signal increases accordingly. And of course, if I move the potentiometer to the left, the signal becomes smaller and smaller. Good, everything seems to work fine besides the two problems I mentioned earlier, so let's now temporarily install the module in the rack. Here is our synth rack, where we are going to install the new module, which is going to be installed on the lower shelf to the right of the VCO and the LFO. Before doing that, however, I am going to get rid of this temporary module, which only scope was to provide control voltages to be used as offset for adjusting the pitch of the VCO. Now that we have the control voltage processor with the capability of adding offset on its own to the DC mixer, this temporary module is no longer needed. So I am going to remove this module and I am going to slide to the left the VCO and the LFO, so we can put the new module directly on the right side. Let me do that first and then we'll continue. Ok, the temporary module is removed, and I have shifted the VCO and the LFO toward the left, putting the LFO closer to the edge. The new control voltage processor module is right here, ready to be connected to the power supply and installed. I am going to connect first the two power supply cables to the PCBs of the module, and then I will connect the other end of them to the power supply bus of the rack. Before attaching the module to the rack, however, I'll make sure that the power is actually reaching the circuits. One way to do so is just to connect the VCO output to the voltmeter and see if the LEDs turn on. Well, that worked, and so let's start prepping for the screws. And then insert the first two. After tightening them up to hold the module in place, I will prep the holes for the remaining screws and I will put them in. The module is now installed and it is time to test it with real control voltages coming from the other modules of the rack. I am starting by connecting the control voltage output of the keyboard controller to the voltmeter. The keyboard emits 1 volt per octave, and so if I push its keys at 1 octave distance, I should see the LEDs light up one after another. And that's exactly what happens. The second C, the next, and the next. Perfect. Let's now test the glide. I have connected the gate of the keyboard controller to the VCA input corresponding to the triangular wave of the VCO, so this way we can control the VCO output. The control voltage output of the keyboard controller goes instead to the input of the glide, while the output of the glide controls the VCO. I have also set the glide to the minimum time in the fast range. And here is how the notes on the keyboard look like. Now I have set the time half the way, which should cause us to hear a size difference in the behavior of the keyboard. Let's increase the time even more. And now with a slow range. Listen how the change from one note to the next has become. And now let's test the sample and hold circuit. The control voltage output of the keyboard goes into the input of the sample and hold. The output of the sample and hold goes to the input of the VCO. I have disconnected the gate cable for now, but the trigger output from the keyboard controller is now connected to the trigger input of the sample and hold circuit. To be able to hear something, I will increase manually the output level of the VCO. The sample and hold switch is currently on the off position, and so, if I play the notes on the keyboard, I shall hear them as usual. But now, as soon as I turn on the sample and hold device, the notes I play on the keyboard are held even if I release the key. And you can hear that effect we talked about before, that the control voltage increases unexpectedly after releasing the key, with the effect that the pitch increases on its own instead of remaining constant. Well, we'll take care of this problem another time. Time to test the limitator now. For that I am going to use the softpot or glider. I have connected the control voltage output of the glider to the input of the limitator, while its output goes to the VCO input. The gate of the glider goes instead to the VCA input of the VCO to let the sound out only while I am using the glider. The control of the limitator is set right now to let the whole signal to go through. And now, if I try to use the glider, the pitch will go from very low to very high. However, if I act on the limitator control, I can limit the upper note produced with the glider. Let's do that some more. So, basically, the limitator allows us to define the highest value of the control voltage, and therefore the highest pitch we can generate on the VCO. We can also do a similar thing at the beginning of the scale of the glider, this time by using the offset provided by the DC mixer. Doing that, we can define a minimum and a maximum pitch on the glider. Let me show you how to do that. So now the control voltage output of the glider goes to the DC mixer input. The output of the DC mixer goes to the input of the limitator, and the output of the limitator goes finally to the VCO. The gate of the glider goes instead into the VCA input of the VCO to control the triangular wave volume. Now we can control the high pitch of the soft spot using the limitator, and we can control the lower pitch of the glider using the offset of the DC mixer. In this other test, I have connected the control voltage output of the keyboard into the DC mixer, so I can adjust the offset through the corresponding mixer control. Then, the output of the mixer goes into the glide input, while the glide output goes to the VCO input that controls the pitch. The gate of the keyboard is connected to the VCA input for the triangular wave of the VCO, so we can hear the VCO output only when a key on the keyboard is pressed. This way I can control the glide time and also the offset from the mixer. Playing with these two controls, I can do something like this, for example. Let's now play a little bit using the sample and hold capability. And at the sound of these notes, I take my leave. Remember to subscribe to the channel and enable the notifications to avoid missing future episodes. And as usual, happy experiments!